Okay.
All right. So the last time we met, we talked about temperature gradients, and there are two gradients in an atmosphere. There's the pressure gradient, dPdr minus equals minus g rho, and then there's the temperature gradient, which had this constant out in front of it that included the surface gravity, it had the opacity in it, it had the pressure in it, all these other things, if you remember right. Now, I hope you all saw that I was able to find the small error with the beta in the equation of state. Got my email on that, and then I made a comment on that on the video at what time it was in the video, saying, oops, this is backwards. Okay. Okay, so anyway, I think we're good. And then with the temperature gradient, we found out that temperature is a measure of energy. It's supposed to give us something about the intensity distribution, number density distribution as a function of frequency of the photons. And it gives us, when you're in thermal equilibrium anyway, in addition, gives us the kinetic energy of the gas. The pressure comes directly from that, so the density and the pressure. So it's connected to the energy, and therefore any change with position in the gas means that it's going to depend upon how the energy changes with position in the gas, which means the temperature gradient depends upon the energy transfer mechanism occurring in the gas. We came up with three types that we talked about. One was the ideological version called adiabatic. It is an ideal, and basically the work done by the gas to expand the bubble as it rises is equal to the loss of energy inside the bubble. So the total heat content, work plus internal energy, remained fixed. It's also called a constant entropy, dq equals 0 approach. Under those conditions, we were able to show that you can derive a gradient that is just a function basically of beta, the ratio of the gas pressure to the total pressure. Okay, fine and dandy. Then we talked about the temperature gradient in terms of radiative transfer. So if you're in a situation where the mean free path of the photons is very short compared to the changes in the temperature, we have what's called the diffusion approximation. And we were able to show under the diffusion approximation that the gradient, the del sub r, depended upon 1 over the opacity, the mean opacity in the gas, so that it was basically proportional to the mean free path at some point. It also depended upon the density, so we wrote it in terms of actually something called the mass absorption coefficient, which has units centimeters squared per gram, so it's kind of a cross-section per unit mass. Okay, which, remember, if you remember right, the opacity was equal to the density times the mass absorption coefficient. Okay. Now, it turns out that is if your energy is only transferred by temperature or by radiation. But in certain regimes where you have convection, the convection is not idealistic, it is not perfectly adiabatic, it doesn't have constant entropy. In fact, as the bubble expands and does work, the internal energy goes down faster than would be done equal to the negative of the work, because at the same time, that bubble, there's radiation in it, and some of the radiation is lost to the surroundings from the bubble. So you have two energies being decreased, energy of radiation loss and then energy lost kinetically from the gas due to the work of the bubble expanding. So we came up with what we call the super adiabatic gradient. And then I talked about the fact very, very quickly, I just zoomed through it because we have other material that's more pressing to talk about, how you figure this out in terms of something called the mixing length model, and you can eventually derive some equations based upon some physical assumptions, derive an equation that only depends upon local variables, which is what you want because you can handle local variables in a gas. That's everything's local variables. Allows you to actually solve the gas. And so how we came up with a cubic equation and showed how you can solve that cubic equation to get the actual temperature gradient in a super adiabatic regime of the atmosphere. And then we briefly talked about the condition called the Schwarzschild condition. It's not on the video very well because I only pointed to the notes, but it's on the notes. The Schwarzschild condition for when you become unstable to the adiabatic process. Now, the way to think about that is you have a buoyancy force on a bubble. Whenever that buoyancy force is positive, you're unstable to convection. And so basically those equations where the adiabatic gradient is greater than or less than to the radiative gradient is a way of saying the forcing buoyancy force is positive or the buoyancy force is negative, the two regimes. Okay. But it all hinges on when the buoyancy force is positive, you're unstable to the gas rising. You're unstable to convection. Okay. Schwarzschild criterion. Okay. So we have the basic idea now that, excuse me, the gradient of the temperature is now dependent upon the energy transfer mechanism, and that for the radiative gradient in particular, it depends upon how radiation is transmitted or transferred. So now it's time to do a little bit of radiative transfer. All right, so I want to do radiative transfer today, and then I want to, when we come back, excuse me, talk about the Gray approximation and how you apply it to the actual stellar atmosphere so that you can get ready to do your model. What I'd like to do is have everything in place so that if you do have time over the break, that you could work on it if you have the time, and not just wait till after the break. Not that I want you to have to do a lot of work over the break, but at least maybe can think of how to do it. Okay, so what we're going to do then is talk about the radiation field. We've talked about the particle field in great detail, and in fact, when you solve this last homework assignment, you basically will become masters of having solved the particle field through density conservation and charge density conservation. Those are the two principles. But now we have to talk about the radiation. How have you had? Who's had the ISM class with? Okay, so 4 of you, but the 3 of you have not. Okay, and so I would imagine that you've seen some radiative transfer through Renee. Okay, and how many have seen some radiative transfer in John's classes? Not very much, a little bit. Anybody, anywhere else that you've seen it? Radio. In radio, okay. Again, Renee. So you might have known that what Renee showed in terms of formalism was a little bit different than what he showed in terms of ISM formalism. We're going to go with what is the typical formalism for stellar atmospheres. Okay, so I hope it's useful. Okay, so we have this first page which defines the radiation field. And what I'd like to do is introduce to you the specific intensity, which you've probably heard of before. Okay. This is what the fuss is all about. Okay. Now, believe it or not, the radiation field is a vector field because a photon not only has a speed and carries a magnitude of energy, but it has a direction. Okay? This here is an incremental amount of energy. This energy is going to be in ergs. Okay? This is units of centimeters squared. This is an area okay, that you have, dA. And so you have radiation coming through this into some solid angle. That radiation is defined in terms of this amount of specific intensity of electromagnetism, okay? And it comes through this area, dA, into some solid angle, okay? It is only monochromatic. It's in some unit of, it's defined as having some wavelength between lambda and lambda plus d lambda, okay? And when it passes through this area at some point in time between t and t plus dt. So basically, it's a very infinitesimal amount of radiation. Now, notice that this radiation is coming through with a direction. We're always going to call the direction, and that is the direction of this actual arrow here. I'm extending it. We're always going to call that the S hat direction, S being the line of sight. Okay, so our formalism is always going to be S hat is the line of sight direction. Okay, and we're going to use N hat as the area of the area element. So basically, you have this little increment in some unit, crossing some unit area, in some wavelength band, lambda to lambda plus d lambda, in some time band between t and dt, into some solid angle band, d omega. The S hat is the direction of the photon, okay, and the N hat is the normal to the area that it's passing through. So this is S hat dot N dot, okay, which ends up being the cosine between these angles, really. Okay. So this ends up having units, and it should be pretty simple to figure out. Erg, okay, and then it's per unit area, centimeter minus 2, per unit solid angle, steradian minus, well, let's see, I can do steradian minus 2, or it's radians minus 2, or per steradian. Which do you prefer? Which do I use?
Use radian.
I use steradians. Okay. So a steradian is basically radian squared. Okay. And then it's per unit wavelength, and it's per unit time. Okay. So normally it's written in the order of erg second minus 1, centimeter minus 2, steradian minus 1, angstrom minus 1. And you might be thinking, my God, who invented that? Okay. Did Rene introduce the specific intensity? Did he introduce it?
Yeah,
he did. Okay. So it seems like it's a very, very complicated, but in the same way that we had to define everything really well defined in the particle field in order to be able to solve all the charge conservation and density conservation and equate it to the equation of state with the state variables, pressure and temperature. It's the same thing if we want to be able to do the same thing with the radiation field. The thing is, the radiation field is more complicated because it's a vector field, okay? And so when we're talking about an area, we might be talking about, we have the surface of a star, and it has some area element which has a normal in that direction, and we want to talk about radiation that's going in this direction toward, say, the observer. So we have to be able to account for that, because radiation's coming off in all directions out of that area element. But as observers downstream that way, we're only interested in the radiation that comes off at this angle, right? So there's a specific intensity here that depends upon the thermal conditions, and then there's some orientation at which we're going to be observing it through. So that's why we need all this information. And then, of course, we might observe it at some wavelength, and we might observe it at some given time. It might be time variable. So this allows us to count for everything. Okay? So that's what these diagrams are basically showing down here. Okay. Now, let's put this area element into context. You see on my diagram here, there's a star. Okay. We've got some axis system. Nope. Let's get it right, Chris. Okay. Now what we're going to do, even though it's on its side, I want you to think of this as the polar axis. Okay? So this is basically Z. And then if that's Z, you want a right-handed system. That's X, that's Y. Okay? So in terms of vectors, this is the k hat direction. Right? This is the I hat direction, and this is the J hat direction. All right? Now, this sphere has some radius r. All right? And then I want to talk about some area element here. Okay. Now, phi, theta goes this way because theta goes from the polar axis down that way. So this is theta equals 0. This is theta equals minus 180 degrees, or basically pi. This is pi over 2. Okay. And phi is basically starts here at the x-axis and goes around this way. Okay, 2 pi. Okay, so this is basically the d phi here, and this is basically the d theta there. Okay, and on this area element, you might have a radiation that comes out. All right. What we're going to do then is we're going to make a special assumption always, because it turns out that all the math simplifies if you assume that the observer is downstream here on the z-axis. Okay? If you assume that, it always makes life easier. That being the case, what are the direction of the photons that are coming off that sphere, that come off the sphere in all directions? Now, they're not all going out radially. At any area of element you pick, they're going out in all directions, right? This some going out this, some there, some there. The only ones that you're going to observe downstream are the ones that actually exit the star precisely in the direction to you as an observer. Okay? It's the light reflected off that door there. I only see the photons that are reflected directly into my line of sight. You guys see the door too, because some of the photons reflect off in your direction. But if I want to calculate the flux coming off that door that I observe, it has to be only the photons coming in my direction. I can't tell you what's happening in your direction. Okay? We're out here along, we've defined it to make it simple. We are out here in the k hat direction. So we are only going to see photons for which s hat equals k hat. Photon that comes off in that direction, we're never going to see. We can't measure it. Okay. Now, let's look at the plane of the sky. I'm going to try to do this best I can. All right. That area element is going to project onto the plane of the sky here, like that, where this distance here is actually r sine theta. This distance here is r sine theta. Okay. Theta is an angle that goes like this, right? So where this projects to, this is on the surface of the star, and then we want the projection above this axis, r sine theta. Okay? And then the d phi still remains as d phi. Okay? So the projected area element now, okay, dA, is what we're actually going to be interested when it comes to understanding how much light comes through the real surface area element. Okay, what is the area of this surface element right there? dA. Whoops. Is that right? Right. Okay. Right. So the reason that you see this is because this is the equation that shows you that projection looking at it. There's something bothering me here. This actually is, if you look straight down radially, that's what it is. Right. Right. That's correct. If you're looking straight down radial at it, that's what it is. Okay. And I believe that this was my argument for why you get the r sine theta. Okay. By the r squared. So here you get the r sine theta, and here you have the d phi, r d phi for this area here. So you get r sine theta, and then there's a d theta there. Okay. All right. So basically have an area there, r squared sine theta d phi. Okay. Now, the thing is that if you want to now estimate something called the solid angle of this, what is it? Okay. Now, there's something else I forgot to say. A lot of times when people try to solve radiative transfer problems, they put the origin at the observer. Let me tell you right now, everything we're going to do, and every problem that I would ask you to solve, if I was going to ask you to solve some homework on this, which I'm not going to because, no, we need a 2-semester class for that. Solve it from the origin of the source. Have you noticed so far as we've talked about it, we started with the source and we put the origin of the coordinate system at the source. Okay? So, given that this is the area element, the true area element on the star, okay, we now want to know what's the solid angle. Okay. Now, solid angle, okay, is defined as over the distance to that area element. Okay? So there are multiple solid angles that you can get from that area element. The area element is the area element is the area element, but the solid angles depend upon where you're talking about from. In other words, since there's a distance dependence to a solid angle, it depends on where you're looking at that area element from. Okay, so let's ask the first thing. What if we look from the center of the coordinate system? Okay, basically x equals 0, y equals 0, z equals 0. In which case, d, the distance from the center to the area element, is the radius of the object. So in that case, d omega is equal to r squared sine theta d phi divided by, what's the distance to it if we're here? R, distance squared. So the dA, it becomes sine theta d phi, if from the center of the source. Okay? Fine. Okay. What if you're out here at some distance, capital D? D observer. Well, in that case, d omega is equal to dA over d squared okay? So what have I just told you? What is that? That solid angle is what you see as an observer. You are here out at some distance d. You're looking back at the star. You're seeing this little solid angle. I'm sorry if the colors are bad. This d omega of this surface area on that star, that solid angle, is the area, projected area that you see, divided by the distance squared to the surface of the source. Okay? So even though we're going to put the coordinate system here when we solve all our equations, put the center of the coordinate system, we can still get what the solid angle looks like to the observer. Okay? Because in the end, the flux that we observe coming out of that surface area element depends upon how big the solid angle is. Okay. All right. So that's what I'm trying to show there. Okay. All right. Now, there's one more thing that we need to add to this, and that is that this is the area element as seen parallel to the in-hat direction. Okay? The area element actually is modified in size by the direction from which you're looking at it and the direction of the surface area element itself. So in other words, if I have an area element like this and I move it like that, you don't see as much of it anymore, do you? The area element that you see in projection. Okay? Is that helping? Maybe I should use my wallet. Here's an area element. Okay? And then if I move it along the sphere, now you don't see any of the area element, do you? What's the angle between you and the normal? 90 degrees. Okay, now 45 degrees, the area projection that you see now is mitigated by cosine 45 degrees. Now, you see the full area. Okay, so the area element size changes with that dot product between the direction of the observer and the direction of the photon, or I should say the area normal, excuse me. And so we have to add now the final thing, which is that the d omega observed by the observer is basically r squared n hat, and I'm going to put an s hat here, and I'll tell you in a minute why. Does everybody follow that? I can't say I did a good job of teaching this today, but I think I got to the final result. All right. Now, I put a K hat and an N hat in here, but what I really want you to realize is I put a K hat here because we define the observer to be a K hat. The observer, this is something that's going to be important about all the mathematics we do here. K hat, S hat is the direction of propagation of the photons. If you're talking about photons you're observing, you are always in the direction of S hat by definition. So if we put the observer at K hat, then we're only talking about S hat equal K hat photons. Has to be. So whether I put a K hat here, that's basically assuming that we've replaced the S hat with a K hat because the observer's in the K hat direction. They're interchangeable. Okay. All right. So if you have S hat, then you could say, well, if we're talking about photons in this direction, then it's the angle from there to there. But now we have to figure out what direction that is in terms of I hat, J hat, and K hat. So we would write S hat in terms of I hat, J hat, and K hat. Okay, it's a unit vector. All right. Okay. Are there any questions about that? I think I did a crappy job of teaching that. I'll put that on film too. So let's define some more things about the radiation field. Let's define something called the mean intensity. Here's a point in space. Here's a sphere around it. Let's call it a unit sphere. Okay? All right. We're going to define what is the mean intensity inside that sphere, centered on that point. Well, this is a certain area, right? This is a certain solid, relative to that point, this is a certain solid angle, 4 pi, solid angle. So we're going to talk about what is the total mean intensity given the specific intensity that's emanating or passing through that point, okay? Passing through that point, centered on that point, but passing through the point. Okay. What is the mean intensity inside that sphere? Okay. Well, we're going to call that J lambda, and we're going to say what we need to do then is integrate over that whole sphere. Okay. And then we're going to weight it by the total solid angle through which it's passing. Remember, this is how you get the mean. You take some distribution and you weight your variable by it. We're going to use the notation like this. And it turns out, if you do the math on integrating over the entire surface for d omega, remember this is a unit source, so r is 1, then you get 1 over 4 pi times this integral. Okay, now remember d omega is a function of sine theta, or theta and phi. So far, we've got this I lambda, but I lambda could have different intensities in different directions. So that's why we have to keep that in the integral, because we're integrating over all the different directions. The magnitude in the theta equals 0 direction could be different than the magnitude in the theta equals pi direction. But guess what? If it's isotropic, so that the magnitude is independent of angle, look what happens. If it's isotropic, So you have to do this integral if it's not isotropic. If it's isotropic, it breaks down that the mean intensity inside of a sphere is actually equal to the specific intensity itself. Okay. Okay. Now, here's a harder one. Flux. Okay. You have some area element there on, say, the surface of a star, and you want to know what's the flux. Okay. And you're way out here at some distance. Well, you want to know the flux. In a sense, what you're doing is you're taking this particular integral, but remember that there's sort of an implied s hat dot n hat from the, if you're at distance d away from this thing. All right, so let me get this right here. There, the projection of this area, the omega that you use is the observed one. Okay. And so this actually is I lambda times s hat dot n hat times the sine theta d theta d phi. So the angle, let's say this is also equal to theta, because why? Because we used k hat. If we'd used x hat, we'd have to know what the phi and the theta is. But we put the observer on the polar axis of our coordinate system, so n hat and theta hat is the same as k hat and s hat are the angle is theta. This is cosine theta. Okay, so this was d omega observed, but this would be the d omega of the area element itself times the cosine theta. Or another way to do that is to say because remember what I've done is I said this is d omega, but d omega observed is equal to s hat dot n hat times this d omega. Okay. You guys. Okay. So basically, you come up with the flux being this very simple integral that it's I lambda cosine theta d omega, where d omega sine theta d theta d phi. Now why did we get a cosine theta term here? Only because this dot product between the area element and the s hat direction of the photon propagation is equal to the angle theta as well, because we set up our coordinate system so that this was the z-axis. Okay, and so that angle theta along the z-axis is also the angle between, because s hat is parallel to k hat, parallel to the z-axis, so that theta becomes the angle between the normal. Okay. So a lot of times you'll see this written in books. I lambda equals cosine theta d omega. But you don't realize, because they never talk about it, but the reason it's so simple is because we're assuming the observer is along the z-axis of a spherical coordinate system. All right. If you don't assume that, if you put the observer at the x-axis direction, you would have come up with the dot product of n hat and s hat being n hat dot k hat, or I hat. And that is not, that's equal to sine theta cosine theta something, right? So why would you want to add an extra sine theta term to your flux statement here when you could just make it it just simplifies the math by defining the observer along the k hat direction. Okay. All right. So that's the sometimes I write this integral as a d omega because basically if you're talking about this area element, you're not integrating over the whole star. You might just be it's over some d phi and over some d theta, okay, and just for that area element. But what's going to happen eventually is what's the side of the star that you can see when we finally want to figure this out? You can only see this hemisphere. You can't see that hemisphere. So eventually what we're going to do is we're going to integrate over theta equals 0 to pi over 2, and then we're going to rotate that integral over 2 phi to get the total flux coming off the surface in our direction. Okay. All right. So I want to introduce to you the astrophysical flux. The astrophysical flux is the flux coming off the surface of the star that can be intercepted by the observer. Let me say that again. The astrophysical flux is the surface flux, the flux out of the surface, okay, that's coming out in the direction of the observer. Now, can you see if a photon's going this way, are you going to see it? If it's going that way, you're going to see it. If it's coming out of the back side, are you going to see it? So you can only integrate 0 to pi over 2, and then 2 phi rotation. That's the surface, okay? So basically the astrophysical flux, I'm going to call that at some wavelength, is 0 to 2 pi for the phi integral, 0 to pi over 2, the observer side of the hemisphere, of I lambda, cosine theta, sine theta, d theta, d phi. Okay. Well, I've got the little bit of math here, okay, and basically, as long as I lambda is isotropic so that it doesn't depend upon what phi or theta direction you're looking at, it pulls out of the integral, okay, and the integral turns out to be, lo and behold, pi.
One question.
Yeah.
So you said the surface flux of the hemisphere facing you, but then in your diagram you said you're only looking at the top half of it so that you can then rotate it all the way around. So is it?
What does this say, top half?
You mentioned that you're only doing 0 to pi over 2, which is right.
And then you rotate.
Right. So you said the astrophysical flux was the surface flux of the hemisphere that was facing the observer, but wouldn't it just be half of the hemisphere that's facing you? Or is it all of the hemisphere that's facing you?
Well, I guess I don't know. The answer is that any part of that surface that's visible that has a line of sight to you. you're integrating over that. So it's effectively the entire, you know, it's like if I held a basketball up here, you would see the entire hemisphere of it.
Right.
Right. So that's what you're integrating over.
But if you're only doing 0 to pi over 2,
Oh, well, if you did 0 to pi, now you'd be integrating over the backside.
right. So if you're only doing 0 to pi over 2,
But then you're rotating over 2 pi.
right.
So it's basically you have an area element that might be up here at pi over 2, but then you're going to look at the band all the way around it.
Okay.
Like if you went to pi and then integrated over 2 pi. Or, yeah,
You would be integrating over the entire surface of the sphere if you went to pi here.
No, that's not what I'm saying.
Oh, I'm sorry.
So I think I might be wording it kind of weird.
Okay.
So the intensity that you're using for that equation should only be the intensity from 0 to pi over 2, right? Because then you rotate it around all of phi.
Right. I mean, this I lambda could be a function of phi and theta. So in other words, there could be bright spots and there could be dim spots. The temperature variation could be such that, you know, you have more intensity at this theta phi and less intensity there.
Okay.
So, and that's true at any location theta and phi on the surface.
Okay.
So you could have a sunspot, for example, where it's cooler. And so the flux that's coming out of there in your direction is going to be smaller magnitude than the flux over at this theta phi.
But why are you even looking at intensity below theta equals 0?
Theta equals 0 and theta equals pi over 2.
Yeah.
And then why are we rotating?
Never mind. Never mind. I think I'm just asking the question weird. It's not coming across right.
Okay,
It's okay.
I apologize.
No, it's fine. I think it's my fault.
Okay. If you want to talk about it offline, I'm perfectly happy to,
Okay.
because I'd like to know what you're asking about.
Yeah, sorry.
You know, because I'm always interested in the physics of what's going on. But if you're integrating over this hemisphere, and if you're isotropic, so that you're not a function of theta and phi, you can pull this out of the integral and you get basically the astrophysical flux is pi times the specific intensity. Now this is assuming that the temperature is constant everywhere in the star, that the specific intensity coming out of this star is completely isotropic on the surface. Okay? And you're catching only one direction of all of that, less the cosine theta, okay, for the projected area. And if it's isotropic, you just have a geometric factor of pi. So basically that's telling you that the flux actually emanating from the surface, all in that direction. All right. Here's my wallet. There's flux emanating it in all directions. I have it at this angle right here or something like that. And we're just capturing the flux that's going in this direction. But we're asking, what is the flux on the surface? Okay. Later on, we're going to say, what's the measured flux that you measure downstream? Okay. But this is the flux at the surface, coming through the surface area itself. But only the flux going through this exact direction of the surface, such that it eventually goes in your direction to the observer. Okay. All right. Sometimes people get really, you know, it's one of those questions I like to ask on a test. You know, please state what the astrophysical flux is in words. And it's really interesting. It's a concept that bends people's minds a little bit. Okay. Now this is the equation for the surface flux. Notice that there's no dependence upon the radius because we're using the d omega on the surface, okay? And there's no dependence on the observer distance. but we said that the observer one, if you're a certain distance away, okay, we said that that was equal to r squared over d squared times s hat dot n hat d omega. So what we basically are doing is we're going to do the same thing. We're going to calculate the flux integral. It's the d omega that you have to change. Remember I said before, the d omega depends upon where you are. Okay? Now, when we did the surface flux, the d omega we used was basically the d omega at the surface, but we wanted the observed one because we're only talking about a component in one direction to the observer, s hat direction, which we call k hat. Now what we're going to do is we're going to say, well, we only want it in the direction of the observer, s hat is equal to k hat, all right? But we're observing it from off of a surface of a source that has radius r, and we are some distance d away in that direction. So now what you get is you get the flux that's observed, okay, is the same area that you're integrating over. Okay. But now you have r squared over d squared. And this is basically your cosine theta, and this is your sine theta d theta d phi. So it's, again, cosine theta, sine theta, d theta, d phi. All right. As you can see now, the r squared and the d squared pull out. You're left with the same integral as you were for the astrophysical flux, which is equal to pi I lambda. There's so many ways to write this. You see why this is very interesting if you think about it now. You have an astrophysical flux that you've measured the surface area, but now this integral is showing you that if you know the astrophysical flux of the source, you know the size of the source and the distance to the source, you now know the flux that you're going to measure. Excuse me. Right? That's a beautifully elegant result. Okay. What's omega again? Well, d omega is dA over distance squared. So omega of an object is equal to the area in projection divided by distance squared. The area of the star is pi times the radius of the star squared. So the omega of the source itself is pi r squared d squared. Pi r squared d squared. So another way to write this, f lambda, is that it's equal to the omega of the source times the specific intensity on the source. That's another beautiful, beautiful, elegant solution. Okay. That basically says, if you know the temperature of a star, and you know its radius and its distance, you know the flux. Right? If I lambda is the Planck function, and therefore you know what its intensity, specific intensity is at that wavelength, and then you're going to say, okay, it's isotropic. I want the flux at that wavelength. If I know the radius of the star, I know the distance to the star. Okay, getting the distances, you know, that's tricky. The radius, well, you know, if we look on the HR diagram, we know what its temperature and luminosity is. For example, we get the radius. Okay. That's for an unresolved source. Okay. It doesn't work for the sun. Because when you observe the sun, it's resolved. Now, I have in my typewritten notes, I don't think I have a section of these in my typewritten notes, but my book, Teched Up Notes, I have a section on how you calculate the flux for a resolved source. And it's very illuminating. Har, har, har. Sorry. But you can also write it as a nice, it's the omega source basically over the omega of a resolution element in your telescope, which is another beautiful thing. So, okay. So I want to talk about some moments of the radiation field. So really what it comes down to, folks, if you're going to solve for the flux coming off of an object, it comes down to, number one, always put the object at the center of the coordinate system because your theta and phi represent what's coming off of the surface. Because it's the geometry of the surface of the object that matters, and for you to understand those projected area elements. When it's a sphere, it's very simple. We've done a sphere. What if it's some kind of weird shaped object and you want to, okay, you have to put the coordinate system and have a model for that so that you know what n hat is at any theta phi position. All right? Put the coordinate system and then put the observer along the k hat direction so that your flux integral is always I lambda cosine theta d omega. Then you have to know what flux are you measuring or do you want to calculate. If it's a surface flux, you're integrating over the surface of the object. If it's the observed flux from some distance d, you have to account for how big the object is and how far away you are from it. So you can see that you have to understand which d omega to put into your integral. That's the key. And that just comes with experience. Effectively, if you are just figuring out what the surface is, the total flux off of the surface, this is it. If you want to know what the flux is off of the surface in a given direction toward an observer only, in that one direction, you have to account for the projected area. And if you want to know not just off the surface, but from a distance d for some object that you have to know the size of now, you use this one. Those are basically the three cases. So when somebody asks you on a homework assignment to calculate the flux coming off of something, hopefully you'll understand now how to do it. Or if you want to make a flux calculation yourself for a galaxy or whatever, you've got that. Okay. All right. I don't want to go through this derivation, but what we've talked about so far is we've talked about we're going to talk about moments of the radiation field now. And the 0th moment is the specific intensity itself. Okay? The first moment, let's see. Sorry. The 0th moment is J lambda, the mean intensity. Okay. The first moment is the flux. Okay. And if you remember, right, that's dependent on cosine theta, with the difference between the direction of the propagation and the area normal. Okay. The second moment is basically what we call the pressure, known as K lambda, and it goes as cosine squared theta. Okay, so there is a derivation here. It's not very interesting, just some math being pushed around, in which you come up with the fact that the pressure itself at a given wavelength is 1 over the speed of light over theta and phi for whatever area element you're looking at times cosine squared of theta d omega. Where this d omega, you know, you have to choose the proper one depending upon what pressure you're talking about. Now, what we do is we write a new integral called K. It's the second moment of the radiation field.
That's radiation pressure?
Yes, this is radiation pressure. Thanks for clarifying. Okay. Now, as you can see, this is related to the pressure. This integral and that integral. So this integral is equal to C times P lambda. All right. This is equal to 4 pi. All right. So in the end, when you tie these two together and the fact that this equals 4 pi, all right, you get this relationship between P lambda and 4 pi over C K lambda. I think you guys can stretch that algebra. Okay. Basically solve for that. Okay. Now, so this is basically the radiation field is the second moment of the specific intensity, which is defined by this. The 4 pi carry through there, and then you get this relationship. So if you have the second moment of the radiation field, you got the radiation pressure through this constant 4 pi over C. Which is nice, because now you're starting to get into physical things, right, from the radiation field. Okay. Now, I'm not going to go through the details of it, but if you look at the top of the next page, where it says the total radiation pressure, you want to take basically the P lambda that we derived there, and we want to integrate that over all wavelengths or over all frequencies. That's what we're doing there. Okay, so you do the substitution right here at the second line. You assume it's isotropic. That means you can pull I lambda out of your integrals, okay, out of the spatial integral. The spatial integral then becomes 4 pi over 3, because cosine squared sine theta d theta d phi is 4 pi over 3 integrated over the full sphere, okay. And then you still have now the 4 pi over 3c times the integral of the specific intensity over all wavelengths. All right. So what people do is they put the pi inside and they say that's pi lambda. Now, if you assume, let me repeat that 3 times. If you assume thermal equilibrium, if you assume thermal equilibrium, if you assume thermal equilibrium, it turns out that the relationship is that I lambda is actually equal to the Planck field, B lambda. You know that special equation that this fellow named Max Planck derived. And when you do that integral over all wavelength or frequencies, you get sigma times t to the 4th. So now you probably wonder, where'd you get that, 1/3 at to the 4th for the radiation pressure? Well, here it comes. All right. So when you do the substitution of sigma t to the 4th for that integral, you get the radiation is 4 sigma over 3c times t to the 4th. Defining now the radiation constant we have introduced in the past as 4 sigma over c, you get the radiation is 1/3 at to the 4th. Only occurs when it's the black body. Otherwise, it's going to be a much nastier integral up here before you make the assumption. Okay. So, all right. Okay. So the next thing we want to do then is we want to introduce to you how the radiation changes with position. So now I've introduced to you the 0th moment mean intensity inside of a unit sphere, what the mean intensity is. Okay. lot of times people talk about the cosmic background radiation, they talk about its mean intensity, meaning if I took a random sphere somewhere, unit sphere, what is the mean of the intensity there? We have the flux, which we said now is based upon the observer position and direction. And then we have the second moment, which translates to radiation pressure through the fact that you're using a force per unit area. Okay. I forgot, there's one more thing I want to introduce to you. It's called the Eddington flux. Okay. It's something that we're going to be using again and again and again. It's called H. It's also the first moment. And I believe this is equal to the flux per unit steradian squared. I don't know why I can't find it. Here it is. It's at this page here where we derive the flux. Okay, the astrophysical flux, and below that the Eddington flux. I skipped it, I apologize. Okay, so basically the Eddington flux is basically this integral. If you don't mind, I'm going to use the erasure method. It's the first moment, the cosine theta, which is used for the flux integral, divided per unit solid angle, and you call this H. So basically, this is the flux per unit solid angle. It's called the Eddington flux. All right. In an isotropic situation, okay, Eddington. In an isotropic situation, it's just the flux divided by. Now, the reason that we define the Eddington flux is because when we get inside the stellar atmosphere, it becomes a very useful measure. Okay, my apologies. All right. I can see you guys are just like, I'm so done. I wish I was with a student who will remain nameless because that's on video. Whatever they're doing now, you all wish you were there too. Okay, so that's what the top of this page is doing, and when we come back, we'll talk about the equation of radiative transfer and solve it. And then we're going to move on to what's going on inside how to get the temperature gradient from all of this. All right, so what do we have here? Just as a quick review, we have the specific intensity. We have the mean intensity, the 0th moment. Okay, we have the flux, the first moment. We have the Eddington flux, which is the first moment as well. Then we have the astrophysical flux over the half hemisphere of the stellar surface, only of those photons in the direction to the observer. And then we have the momentum, which is related to the radiation pressure, called the second moment. Okay? So that's what we've covered today. And I don't know how much of that got covered in Renee's class, but it turns out that when you solve the atmosphere, you're not going to need to include all of these things in your atmosphere. Don't think that. But when you finally want to get out the simplified equation at the end that helps you solve the atmosphere, you have to account for the moments of the radiation field in addition to just what the specific intensity is as well. Okay, so that's why we introduce this. All right. Okay, so we come back, we're going to do how the radiative transfer works and solve that transfer equation. And from there, we're going to move then into what's called the Eddington method, if you will, to get the temperature gradient in a gray atmosphere. It's a very simple expression. And then you'll have all the ingredients you need. Okay? Okay. Thanks for listening.